So we'll continue our discussion related to capacitance and capacitive circuits. Okay, so the next topic is an isolated spherical conductor, the capacitance of an isolated spherical conductor. So let's say we have a conducting sphere of radius r carrying a positive charge q in isolation. Okay, isolated positively charged spherical conductor of radius r. The capacitance for this spherical conductor is given by C is equal to 4 pi epsilon 0 r. Okay, if it is in air or free space, and if it is in any other medium, the capacitance is given by 4 pi epsilon 0 epsilon r, where epsilon r is the relative permittivity or dielectric constant of the of the medium in which the spherical conductor is placed. Here I am not going into the derivation thing. Okay, the derivation I am not going. I am assuming that you have some background knowledge about it. This is just a quick review because these things will come in our discussion related to parameters of transmission lines, okay, in power systems engineering. Okay, so here I am just going through a quick review of the basic concepts which will come into play in our discussion related to transmission line parameters. So for an isolated spherical conductor, the capacitance is given as this. Then we have a spherical capacitor. So a spherical capacitor, it consists of two concentric hollow spheres. So here the two spheres are A and B. A carries a positive charge on its outer surface. It has a radius r subscript a. B carries a negative charge which is induced on its inner surface because of the positively charged sphere A. It has a radius rb. So A carries a positive charge plus q, B carries a negative charge minus q, same magnitude, opposite sign. Another important thing, the outer surface of sphere B, the outer sphere, that is earthed. Okay, so the positive charge which develops on the outer side, it goes to the earth. Okay, so this is the basic construction of a spherical capacitor. So the capacitance of a spherical capacitor is given by C is equal to 4 pi epsilon 0 Ra Rb divided by Rb minus Ra, where Ra and Rb are the radius of spheres A and B. Epsilon 0 is absolute permittivity. This is for air or free space. If it is placed in any other medium other than air, then the relative permittivity or dielectric constant comes into play. So it becomes 4 by epsilon 0 epsilon r Ra Rb by Rb minus Ra. So this is the formula. Again, I am not going into the derivation. I am simply putting the direct concepts so that you can, if you have any confusion when we go into the actual discussion of transmission line parameters, you can come to this. So the detailed derivation, that is the different thing, electrical circuit analysis or network analysis, that is the discussion for that. For power systems point of view, I am simply stating the direct things without going into the detailed derivation. Then is cylindrical capacitor. Again, a very important topic. So a cylindrical capacitor, it consists of two coaxial cylinders of different radius. Okay, same principle, only the shape of the two conductors are different. So we have a cylinder A of smaller radius and a cylinder B of larger radius. The inner and outer cylinders A and B of radius A and B, small a and small b. So there is a positive charge on the outer surface of the inner cylinder A plus q, which induces a negative charge on the inner surface of the outer cylinder B. So the positive charge which develops on the outer surface of the outer cylinder B, it is earthed, so it goes down. So we are only left with these two conductors with opposite charges of equal magnitude behaving as a capacitor. So the capacitance of a cylindrical capacitor of this kind is given by 2 pi epsilon 0 L by log B by A to the base E. So L is basically the length of the cylinder. Okay, L is the length of the cylinder here. L is the length of the cylinder. This. Okay, the length of the cylinder. So here the capacitance is directly proportional to the length and the inner and outer radius, the log of that to the base E, and this is the thing. Okay. So next is grouping of capacitors. So the different ways in which multiple capacitors can be connected. So there are two ways in which they can be grouped, similar to resistors. First is series grouping, next is parallel grouping. So series grouping of capacitors. So multiple capacitors, they are said to be connected in series when the charge on each plate is the same, or the same current flows through it. So the series equivalent of multiple capacitors connected in series, here C1, C2, C3 up to the nth capacitor connected across a potential difference V, that is given by 1 by Cs, where Cs is the series equivalent, that is equal to 1 by C1 plus 1 by C2 plus 1 by C3 up to the nth capacitor. So the reciprocal of the individual capacitances. So here, not going into the derivation, simply directly I am stating to review. So parallel grouping, so capacitors are said to be connected in parallel when the potential difference across each is the same and different current or different charge flows through each of the capacitor branches. So the parallel equivalent capacitance for multiple capacitors connected in parallel is given by Cp is equal to C1 plus C2 plus C3 plus Cn. So it is the opposite of resistance. In resistance, when it is connected in series, they are added, the individual resistances, and when they are connected in parallel, the reciprocal of the individual resistances are added. But here it is the opposite. Next is the energy stored in a charged capacitor. So for a capacitor C with charge Q, that is plus Q minus Q on the different plates, opposite charge of the same magnitude connected across a potential difference V. So the energy stored in the electrostatic field, that is given by U is equal to 1/2 CV square or 1/2 QV, because Q is equal to CV, so that becomes QV, or again Q is equal to CV. Okay, so V is equal to Q by C. By substituting that, we get 1/2 Q square by C. So these are the different ways in which the energy stored in the electrostatic field of a capacitor can be determined. Next concept is the energy density of electric field. So we know that the basic representation of a capacitor is a parallel plate capacitor consisting of two conductors separated by a certain distance d with overlap area A. So whenever distance and area comes, we have an imaginary volume in which the electrostatic field exists. Okay, so the energy density of that electrostatic or electric field in that imaginary volume, that is called as the energy density, the energy stored per unit volume of the electric field. So here the total energy, that is equal to 1/2 CV square, okay, and the volume of the electric field, that is equal to AD. Okay, volume of electric field is equal to AD. So here we have 1/2 CV square, the energy, total energy divided by volume of electric field, which is equal to AD. So this becomes the energy density of the electric field of the capacitor or the parallel plate capacitor. Okay, next is the concept of common potential. So here what it means, let us say we have two different capacitors of different values of capacitance. They carry different charge. Here it is C1, C2 carrying charges Q1, Q2. They are connected to each other with the help of a switch. In this position, the switch is open. They have different potential values across the capacitor. For C1 it is V1, for C2 it is V2. Now, suppose the switch is closed, what will happen? There will be movement of charges. Okay, the movement of charge from one capacitor to the other till the potential difference across both of them is the same, a common value. Okay, when the switch is closed, there will be a movement of charges from one capacitor to the other. Movement of charges will lead to a decrease in potential in one and an increase in potential in the other till both the capacitors they are at the same electric potential, same potential difference, V, let's say, or VC. Okay, VC. So this VC, the same potential across both the capacitors, it is called as common potential. So that common potential is given by, the common potential VC is given by total charge by total capacitance, which is equal to Q1 plus Q2 by C1 plus C2, total charge by total capacitance. But we know Q is equal to CV. Okay, Q is equal to CV. So Q1 becomes C1 V1, Q2 becomes C2 V2, making the substitutions. We get C1 V1 plus C2 V2 by C1 plus C2. Okay, so this is the expression for common potential. Okay.